Hello and welcome to this clip going through some selected multiple choice LCR chemistry questions. I've chosen these because they're slightly more applied in style. They're the type of question that you see in a multiple choice section that might suddenly slow things down because a bit of processing or thinking is required. So any specific processing techniques or tricks and tips I can think about as they come up, I'll share with you as we work through these. Okay, so this one is about a rather complicated looking structure, ibuprofen it happens to be, and it asks you the number of moles of ibuprofen in a standard tablet. So the first thing to do is to take your structure and convert it to a molecular formula. Now you know how to work out the MR. So that adds up to 205.0 grams per mole. Now, because we know as a standard tablet contains 200 milligrams of ibuprofen, 1 milligram is obviously 1,000th of a gram. So there must be 205,000 milligrams per mole. So because the question mentions its piece of data in 3 sig figs, the answers are given in 3 sig figs, so that gives us 9.71 times 10 to the minus 4, which makes B the correct answer. So here's another one, which is not a calculation based one, but it's got a decoy in there. So let's think about what the information you're given is first. So the first thing is that it suggests the presence of bromide ions. So that allows us to discard 2. Now out of the remaining 2 you have to think quite carefully. What's going to react with aqueous silver nitrate and ethanol? So the clue is buried in amongst that sentence where it says aqueous silver nitrate. That means the water that the silver nitrate is dissolved in is behaving as a nucleophile and then reacts with a haloalkane. So you need to find a bromoalkane. So now we can discard A, because it's aromatic, and as you remember, aromatic compounds do electrophilic substitution, not nucleophilic substitution. So the only option in this one is C. Okay, so this one is about the mass spectrum of an ester. Now you don't actually need to know about esters to be able to work this one out, because it's the mass spectroscopy part they're focusing on, not the ester chemistry. Okay, so what you've got to do here is just work through each one in turn. So the first statement would suggest that the circled part comes off as a fragment. Now does that add up to 45? Now it does. So let's think about that possibility. Now it could be that we've stumbled on the right answer straight away, because it says which statement is most likely to be true. Now there's nothing about that statement that suggests that it's not going to happen. Yes, that fragment could come off. Yes, it has an MZ value of 45. Now the second one can be discounted because you would need 3 carbons in a row, and you haven't got that. Now the third one can't be true because the molar mass is already 88 grams per mole, so the M plus 1 MZ value would be 89. I'm looking at the final one where it says no peak at MZ equals 43. You can see that the remainder of the fragment, the remainder of the ester after you've taken the MZ45 fragment off, is going to be 43. So all of those 3 answers, B, C and D, are wrong. So your answer is definitely answer A. Okay, so this one is essentially Markovnikov's rule, because you've got the major product there. Now someone's using a sander in the background, another just out the window, so sorry about that background noise, but we'll continue anyway. So what we've got to do is visualize this in terms of what would the mechanism be. So the first thing to do is to start off the electrophilic addition, and that gives us two possible intermediates. So now what we've got to do is look at the positively charged carbon atom and how many alkyl groups or how many carbons are attached to that. So you can see that one of them is a tertiary carbocation. So the one on the left hand side, the tertiary carbocation, will lead to the major product. So thinking about what the names of the major product are, you can see quite clearly that this one will lead to 2-bromo, 2-methyl butane. So a little bit of visualization perhaps required for that one before you can arrive at an answer. Okay, so let's move on to the next one. So with this one, it says that the compound below reacts with hydrogen chloride gas at room temperature and pressure to form a saturated compound. So that means all carbon-carbon bonds, carbon-carbon double bonds have reacted. So if we look at the carbon-carbon double bonds, there's 2 carbon-carbon bonds present in your structure. So you therefore need 2 HCl molecules required. So that means 2 moles of HCl needed for every mole of the compound. Now I know that we've got 0.25 moles of the compound, so that means we need 0.50 moles of hydrogen chloride gas. Now if we look at the question, it also tells us that room temperature and pressure is involved. So therefore we know it's a V equals 24N question. And we know that 1 mole of any gas occupies 24 decimeters cubed. So 24 times 0.5 is going to give us 12 decimeters cubed, which in this case is answer D. Okay, let's go on to the next one. Okay, so this one is an organic synthesis type one. So what we've got to do, I think, is probably try to visualize the exact changes in functional groups. So to do that, I'm going to draw out the reaction but using displayed formulae and not structural ones. Okay, so let's take the structural groups one at a time. So obviously you're oxidizing the primary alcohols to make the carboxylic acids. But if you're doing that, you have to realize that going from an alkene to a ketone is not possible in one step. So what you're going to have to do is turn the alkene into an alcohol first. So if you react the alkene with water or steam in the presence of H3PO4, before you do any oxidizing, what that's going to do is turn the CC double bond into a secondary alcohol. So you want to find an intermediate that has a secondary alcohol. So that leads us to C as the answer for this one. Okay, now this is a very, very common type of question where it's quite deductive. So what you've got to do is just read very carefully what the first sentence says. 14.4 grams of an element reacts with oxygen to form 24.0 grams of a compound XO2. So what you want is the number of the mass of oxygen atoms. So that gives us 9.6 grams. Now we need to work out how many moles of oxygen atoms we've got. So the reason I keep underlining atoms is because you'll notice in the compound it's XO2. Now O2 could be easily mistaken for oxygen molecules, couldn't it? The diatomic oxygen, which will lead us down the wrong direction. So what we need to do is to focus on the fact that it's oxygen atoms and it's just coincidental that there happens to be two of them. So that gives us 0.6 moles. So using the mole ratio of X to oxygen atoms in XO2, we now know that we have 0.3 moles of X. So to work out the molar mass of X, which is what we're after, we do the mass over moles, which gives us 48 grams per mole. And by consulting with the periodic table, that gives us titanium, so the answer is C. Okay, so let's go to the next one then. Okay, so this one is another calculation one, and it says the maximum safe concentration of bromine in air is 0.0040 milligrams per decimeter cubed. So the way to deal with this is to convert milligrams into a unit that is more standardized. So grams is the standard unit for mass, so we use grams in chemistry really as opposed to milligrams. So that's 4 times 10 to the minus 6 grams per decimeter cubed. Now what we've got to do is get to the point where we know how many moles of bromine we've got per decimeter cubed. So to do that we've got to work out the molar mass of bromine as 159.8 grams per mole. So to work out how many moles we've got per decimeter cubed, we have to divide the mass in grams per decimeter cubed by its molar mass. So that gives us 2.5 times 10 to the minus 8. Now, if you remember that there are 6.02 times 10 to the 23 molecules in every mole, what we've got to do now is multiply that by our 2.5 times 10 to the minus 8. Now the 2.5 times 10 to the minus 8 was actually 2.503128911, so I've obviously simplified it slightly here. So that leads us to 1.5 times 10 to the minus 6 molecules, which means that our answer is A for this one. So this next one is a Hess's Law question, and the first thing to do is to find out what data you have. So this requires a Hess Law cycle, and the type you use if you have formation enthalpy data is where you have the reactants going to the products. You're trying to find out the delta RH value across the top. So if we put in delta RH on the top and populate the arrows pointing from elements to reactants and elements to products as delta FH, you obviously add them up, so that's why the sum of sign is in front of them. The direction of travel of the dotted line goes against the enthalpy arrow on the left, so you have a negative. That's where you reverse the sign of the values on the left. You keep the sign of the values on the right because the dotted line is going in the same direction as the enthalpy arrow. So I'll use that model in a second when I do the main thing. So I'll leave that little model there, and I'll build an enthalpy cycle underneath the actual equation. So my box at the bottom has all my elements in their correct mole ratios. So I draw in my indirect route, and I can put in my enthalpy data from the table. So now we have them, we can actually follow the indirect route. So I've reversed the signs because the indirect route points in the opposite direction to the enthalpy arrows that point upwards. So that gives me minus 136.5 kilojoules per mole, which is obviously answer B. So let's move on to the next one. So with this one, you've got to just isolate the oxygen as a percentage of the total MR, or the total molar mass of your compound. But the trick here is to write it out as a molecular formula. So now what you can do is take the oxygen, and you can see that that's 160. And if you take all the other separate elements, you can now isolate oxygen and express it as a percentage. So we know that the molar mass is 220.3 grams per mole. So that gives us 72.63%, which is answer D. Okay, so let's do the final one I was going to do on this particular clip. So this one is a bond enthalpy question. So whenever you have bond enthalpy questions, you have to use not necessarily a Hess's Law cycle, but you use a little expression. And I'm just going to show you how to do that. So that's an equation from our textbook. So now what we do is we have to visualize the reaction as in terms of bonds. So now what we can do is put the values that we do have into that displayed formula expression. So we know what the carbon-carbon double bond, the hydrogen-hydrogen single bond, and the carbon-carbon single bond are, because the table tells us. So now what we've got to do is find out the bond enthalpy of the carbon-hydrogen bond. So you can do it algebraically like that. So if we counterpole the carbon-hydrogen bonds in ethene, you can see you've got 4x there, and all the carbon-hydrogen bonds in ethane, you've got 6x. So if we solve for x, we can find that x is plus 413.0 kilojoules per mole, so that can represent the carbon-hydrogen bond enthalpy. Okay, so that takes me to the end of this clip. I just thought I'd go through some slightly more difficult, maybe time-heavy ones with you, just to see how you might be able to process them. Some of which you can shortcut, some of which unfortunately takes a little bit of time. So the main thing to remember, I suppose, with doing past paper question sections in an exam is to get the easy ones done first, and then you can come back and do the harder ones. So get the easier ones done in less time than you need, and then come back and you'll have some time in your top pocket to do the more difficult ones like these. Okay, so thanks for listening, hope it's been useful, and until next time, see you soon.